Hi, my name is Dr. David Noel. I'm a PhD graduate of Nova Southeastern University in Florida, and I will be talking about a paper that was written from my PhD dissertation titled An Investigation of Methods for Improving Spatial Invariance of Convolutional Neural Networks for Image Classification. Dr. Sumitra Mukherjee is my co-author and was also the chair of my dissertation committee. So, what are convolutional neural networks? Well, these are specialized neural networks that are used for detecting and extracting features from images or any feature that has a grid-like topology. Typically, they are used for image classification. One of the most popular ConvNet was called LayNet. It was created by Dr. Jan LeCun several years ago for detecting handwritten digits. Here we see a brief overview of how it works. An image or a handwritten image is fed into the convolution network. It passes through several layers of convolution and pooling, which you will learn about later. And eventually, the features are passed through a fully connected layer at the very end that would classify what sort of digit it is. So a ConvNet basically comprises of three main layers. We have the convolution layers, the pooling layers, and the fully connected layers. In the convolution layers, filters, also known as kernels, are convolved from one end of an image to the other in order to activate certain features from that image. When these features are activated or extracted, a nonlinearity is added to the feature map to add a bit of nonlinearity to the output. The most popular nonlinearity that's used is called ReLU as of now. Then the feature map goes through a mechanism called pooling, where it is further downsampled so that similar features are merged together, which reduces the number of parameters that the network has to learn. And finally, as we saw, the classification layer is the fully connected layer that tends to classify what class does that image belong to. Now, the intuition behind convolution, as we see, involves sparse interactions. Basically, as the kernel convolves the image from left to right, top to bottom, it detects very meaningful information, and so that information is more or less summarized. So what you have is a feature map at the end of the day that has basically compressed an image from being millions of pixels down to maybe tens or hundreds. Another very important part of convolution networks is the shared weights concept. Basically, what it means is if we compute a feature at some position x1, y1 in an image, that feature is also significant at some position x2, y2. So for example, if there's a pen that's shown in the top left of an image, that same pen shown in the bottom right of an image should have the same weights, right? Because it's basically the same thing. And finally, one of the fundamental properties of convolution networks are the equivariance to translation. What that means is basically any changes to the input of a ConvNet should have a similar effect to the output, right? The output should be changed in the same way. Now, what is spatial invariance, which is the title of this topic? Well, spatial invariance is a fundamental property of ConvNet. It basically describes how a model reacts or behaves to changes in its input, which basically implies the model's generalizability or its robustness to change. Any object that is placed in front of a ConvNet, and the ConvNet can realistically, or accurately determine what it is, especially in novel situations, that ConvNet is said to have the property of spatial invariance. And so increasing the spatial invariance of a ConvNet, it reduces misclassifications and improves the predictive capability of that ConvNet. Now, what is the problem? Well, The problem is many authors have shown that convnets are not spatially invariant. And that basically means that very small perturbations in the input can result in significant changes to the network's prediction. If we look at the image on the right here, a study was done by Azule and Weiss, which showed that translating an image downward by a single pixel resulted in as much as a 30% misclassification. This is very bad because it can lead to disastrous consequences, like fatalities in autonomous vehicles or even racial discrimination. So the goal of this study is to provide a rigorous comparative analysis of two advanced data augmentation techniques that are used to improve the spatial invariance of convnets. One of them is called RandAugment, the other is Generative Adversarial Networks. But before we talk about them, let's talk about data augmentation. So data augmentation is a technique that's used to basically imbue invariances into training data sets. And then the convnet, which would be trained on these data sets, would learn these invariances during training, right? In that way, the model's architecture doesn't have to specifically cater for every single invariance during design time, right? Now, the improvement in spatial invariance study will be determined by increases in the test accuracy, the F1 score, and a reduction in overfitting. Now, let's look at RandAugment. So RandAugment is basically a stochastic technique used for data augmentation that applies geometric transforms to images. The transforms does not have to be learned ahead of time, and it can uniformly apply up to 14 transformations to each sample as of this research. Now, RandAugment artificially increases the training set because it does not add new samples to it, it simply perturbs the ones that are already there. Now, on the other hand, the generative adversarial networks, these are neural networks that are used to generate synthetic examples after they were trained on some training set. Now, the idea with GANs is that they increase the invariant space by unlocking additional information from a data set. That's the idea behind them as a data augmentation technique. And so they sort of abstract away the many hand-engineered decisions, during augmentation. Now, generative adversarial networks would increase the training set physically, as you might expect, because they are synthesizing new examples. Now, a conditional GAN would be implemented in this research for experimentation. Now, the methodology. So 45 experiments were done in this study using 5 augmentation policies, 3 benchmark datasets, 2 pre-trained convnets, and 1 basic convnet. So the policies are such. Policy 1, we have no augmentation. Policy 2, we apply RandAugment to the unaugmented samples. Policy 3, we use samples that was only generated from the GAN. Policy 4, we combine the GAN sample and the unaugmented samples. And policy 5, we apply RandAugment to the GAN samples. The datasets are the benchmark datasets MNIST, FMNIST, and CFAR10, which should be well known in the AI and machine learning communities. And the convnets, we use ResNet50, which is a 50-layer deep network that was developed by Microsoft. We use InceptionV3, which is a 42-layer developed by Google. It's a wider network versus ResNet, which is a deeper network. And finally, NoelNet. NoelNet was developed by myself for the purpose of this study, and it's a simple 9-convolution layer network. Now, in terms of the sequence, a data input pipeline was created in TensorFlow, where we would load a data set, partition it into a trained validation test set. Then we would pre-process the samples, such as normalizing between 0 and 1. Then we would configure the dataset using batching, prefetching, shuffling, and augmenting. Finally, we would train the dataset using the training dataset, We would evaluate it using the validation dataset, and we would check its accuracy using the testing dataset, and all of that data would be, all that metrics would be safe to find. As far as some of the resources used, we use Python 3.9, TensorFlow, Keras, Matplotlib, NumPy, Pandas, and a local desktop PC was used in this study with a liquid-cooled CPU, 32 gigs of RAM, and an 8 gigabyte GTX 1080 GPU. As far as the metrics, the following metrics would be used in the study. We have the training, validation, loss, and accuracy, test accuracy, the precision, recall, F1 score, and latency of training for each policy. As far as barriers go, there are no optimal size for training datasets, so this has to be a case-by-case basis. And GANs are notoriously hard to train, so there's no guarantee in the quality of the images they synthesize. And of course, the GANs take a very long time to train. Now, one of the limitations, or the most important one I think here, would be the quality of the synthesized images was assessed by the author, which is myself. And image quality is very subjective. Now, in terms of the GAN, so the first thing we had to do was to create the GAN and train the GAN on the various data sets. So what we see here was we have the MNIST data sets, which was on the far left here. This is the unperturbed samples. The middle one is the augmented samples using RandAugment. And at the end, these are the synthesized samples. So from these examples here, you can see the synthesized samples are very close to the original samples for MNIST and FMNIST. For CIFAR10, some of it looks close, some of it may not be exactly matching the original data set. So this was some of the hyperparameters used for training the GAN initially. Now, what are some of the results? NeuRalNet, which is our basic model, has only 9 convolution layers and that was developed for this work. We see that policies 2 and 4 resulted in the highest accuracies of for the MNIST dataset. We see a same pattern for FMNIST, where policies 2 and 4 resulted in highest accuracies for the tested data. Here, of course, policy 2 is higher. And for CIFAR10, we saw policy 2 being the highest, while policy 3 resulted in the lowest accuracy. Now, in terms of the training loss and validation accuracy here, we see that on the B here, B represents policy 2 in terms of the training loss and validation. And we see that policy 2 had the slowest convergence, the highest accuracy, and minimal overfitting. Right? Overfitting here is gauged by the distance between the training curve and the validation curves. Then we see policy 3 had the fastest convergence, the lowest accuracy, and maximum overfitting. The loss curves for policies 2 and 4 decay slowly, which suggests more sources of invariance. Now remember, policy 2, which is represented by B here, this is the one that uses RandAugment only, while policy 3 is the one that uses generative samples only. Now what about ResNet50? ResNet50, which is a 23.6 million parameter ConvNet, we see a very similar pattern, right? We see that policies 2 and 4 improved the spatial invariance or the accuracy on MNIST. On FMNIST, we saw an improvement again in the accuracies. And on CIFAR10, policies 2 and 4 again resulted in the highest accuracies for the data sets tested, while policy 3 consistently returned the lowest accuracies. Now, in terms of the training loss and validation accuracy, similarly to NeuRalNet, we see policy 2 had the slowest convergence and highest accuracy and minimal overfitting. And again, policy 2 is represented by the B charts in the charts here. We see policy 3 again had the fastest convergence, but the lowest accuracy and maximum overfitting. Now, InceptionV3, which was a state-of-the-art model, again, it's a 21.8 million param model. It's a wider model than ResNet, and what we see is a very similar pattern, where policy 2 achieved the highest accuracies, or the highest metrics, while policy 3 achieved the lowest metrics again. The same was observed with ResNet and NoelNet. In terms of the training loss and validation accuracy, once again, policy 2, which is represented by the B charts here, had the slowest convergence, highest accuracy, and minimal overfitting, while policy 3 basically had maximum overfitting and the lowest accuracy. In terms of the training latency, we see that NoelNet took the least time to train because it is a smaller ConvNet, while Inception took the most time to train. As a matter of fact, Inception took almost twice as much as ResNet in every case. In terms of the highest test accuracy, Poly 2 consistently resulted in the highest accuracy, and we see that the Inception network achieved the higher accuracy on CFAR10 and FMNIST at the expense, however, of higher training time. For each dataset used, we saw that ResNet achieved the lowest accuracy. Now, in terms of some analysis, does data augmentation actually lead to more spatially invariant networks? The answer to that would be yes, based on the experimentation. Why? Because policies 2 and 4 consistently achieve higher accuracy than policy 1, which was the baseline. Then are deep architectures more spatially invariant than wider ones? The results would indicate no, since Inception 3 consistently had higher accuracies and F1 scores than NoelNet and ResNet50. Remember, InceptionV3 was a wider network, while ResNet and NoelNet are deeper networks. Now, does generative augmentation lead to more diverse samples? The results would indicate no, because the samples produced by RandAugment showed more diversity than that produced by the GAN, which was synthesized. Does larger datasets increase spatial invariance? Yes, and that would be intuitive, right? We see this because policies 2 and 4 resulted in higher accuracies relative to policy 1. It's intuitive because larger datasets tend to have larger diversity in them. Now, does stacking augmentation methods lead to more robust networks? Yes. The results indicate that policy 5 constantly had higher metrics than policy 3. If you recall, policy 3 was only the synthesized examples. Policy 5 applied RandAugment to these synthesized examples. So stacking does help. Now, does combining the synthesized and unaugmented samples improve invariance? Yes. And that goes back to a larger data set. The more data we have, the more sources of invariance we can learn. And that is seen by policy 4 consistently being higher than policy 1. Now, does synthesized samples improve invariance? The experiments indicate no, because policy 3 consistently had lower metrics for each experiment, but we will touch base on this in a little while. Does the number of parameters affect the spatial invariance? The results show that more parameters does not necessarily indicate better predictive accuracies. Now, in conclusion, we see that RandAugment is a highly effective method for improving the spatial invariance in ConvNet. We see that data augmentation is more effective than architectural innovations for improving the invariance. We also see that combining synthesized and unaugmented samples increases spatial invariance. We saw that wider models are more spatially invariant than deeper models. They are slower to train. Then we see that stochastic techniques produce more diverse samples than generative ones. And finally, we saw larger data sets lead to more spatially invariant networks. Now, as far as the implications, basically, not implementing any sort of spatially invariant techniques or techniques that can improve spatial invariance can lead to poor performance of the models, especially in novel situations. It can lead to overfitting, larger model size, or limited interpretability. As part of the future work, we would like to use a different sort of GAN to synthesize the images, such as a Wasserstein GAN, or implement generative techniques like neural style transfer. Plus, there are many other augmentation strategies that can be tried, such as cut mix, cutout, grid mask, and not just RandAugment. And finally, we can use more respectable data sets like ImageNet. So at this time, I would like to thank you for listening at our presentation. Any questions you have or any concerns, recommendations, please feel free to reach out to us via our email, which will be provided by the organizers. Thank you very much and enjoy the rest of the convention.